Okay, chapter 15 is on temperature, heat, and expansion. And certainly temperature is something we think about every day if we ever check the weather on our iPhone. So what is temperature? Well, temperature is a number that corresponds somehow to the warmth or coldness of an object. So something might be warm, hot, cold. There's a number associated with all of those feelings. And you can measure that number with a thermometer. So it's a per particle property. Something with more particles doesn't necessarily change its temperature. There's no upper limit on temperature, but there is a definite lower limit, which we call absolute zero. Temperature is proportional to the average kinetic energy per particle in a substance. So for a gas, like you see here, these molecules are moving around with some average speed and giving it some average kinetic energy. If that increases, that will increase the temperature. For a liquid, the temperature is related to how fast the particles are all sliding and jiggling past one another. And for a solid, it's how fast the particles move as they vibrate in place. So a thermometer measures temperature usually by the expansion or contraction of a liquid. Sometimes there's a mercury thermometer, sometimes a red alcohol. But the reading occurs when the thermometer and whatever you're measuring, the object, come into thermal equilibrium. So they have the same kinetic energy per particle. And an infrared thermometer operates by sensing the infrared radiation from the object. So there are three temperature scales mentioned in this book. One is Celsius. Celsius has the very simple property that it's 0 degrees Celsius for the freezing point of water and 100 degrees Celsius for the boiling point of water. And there's 100 degrees in between there. Fahrenheit is 32 degrees Fahrenheit for freezing of water and 212 degrees Fahrenheit for the boiling point of water. And there's no real advantage to using Fahrenheit. It's just a historically traditional scale. Kelvin has the property of 273 degrees Kelvin for freezing of water and 373 Kelvin for boiling of water. This has an advantage in science in that 0 degrees Kelvin is absolute zero. And it has the same size degrees as the Celsius scale, but it has this advantage, it's sometimes called absolute temperature, that it is directly proportional to the kinetic energy per particle. Heat. Heat is a form of energy that is transferred from one thing to another due to a temperature difference. It's energy in transit. And heat naturally flows from high temperature objects to low temperature objects. So for example, this coffee is high temperature and the hands around it are lower temperature, so heat will naturally flow out of the coffee and into the hands. And heat can never flow unassisted from a low temperature to a higher temperature object. So heat can be measured in joules, since it's a form of energy. We also use the unit calorie for energy. It turns out 4.818 joules of heat are required to change the temperature of 1 gram of water by 1 Celsius degree. And we call that 1 calorie with a lowercase c, sometimes measured by burning a peanut. Okay, so energy ratings from foods and fuels are determined by burning that food and looking at how much energy gets released. So another unit of energy is subtly different. It's the calorie with a capital C, okay, sometimes called the kilocalorie. It's 1,000 of the calories defined from the previous slide. And that's the amount of heat needed to change the temperature of 1 kilogram of water by 1 Celsius, as opposed to 1 gram for a lowercase c calorie. Specific heat capacity. So this is a property of any substance. Specific heat capacity is defined as the quantity of heat required to change the temperature of 1 kilogram of the substance by 1 degree Celsius. It's like thermal inertia. Okay? Any substance will resist a change in temperature, and how much it resists it is determined by its specific heat capacity. So this water bottle has a high specific heat capacity, so if it's hot, it stays hot for a long time. So different substances might have different specific heat capacities. For example, iron has a higher heat capacity than silver. So it takes about 2 minutes to raise the temperature of this iron pot to boil water, but if the same size pot was used but made of silver, it could take less than 1 minute to raise the temperature to boiling water. So water itself has a very high specific heat capacity. It's higher heat capacity than almost any other substance, and it involves the number of ways that the water molecule can absorb energy. So you can absorb energy by the jiggling of the molecules, but also internal vibration between the hydrogens and the oxygen, or rotation. So this particular shape of the water molecule allows it to absorb energy without even increasing its translational kinetic energy. So specific heat affects climate in the sense that land has a smaller specific heat capacity than water. So ocean currents can carry a lot of heat from, for example, in the Atlantic, from the Caribbean regions up northeast to warm the Western European countries. Thermal expansion. So when a substance has an increase in temperature, the molecules are jiggling faster, and so therefore they usually move further apart, and that expands the whole substance. So most substances expand when they're heated and contract when they're cooled. For example, railway tracks on a winter day, if they're laid down, if they expand on a summer day, they sometimes will buckle, as shown in this picture. Another example is a trick a lot of people know, which is that if a metal lid is stuck to a jar, if you run it under hot water, it can expand the lid and make it get unstuck. Thermal expansion plays a role in construction. For example, there are often expansion joints that you'll see on bridges, so that if the temperature increases, these interlocking pieces of the joint will close together. On a cold day, they'll get further apart, but the bridge won't have a hole in it. Also, the gaps on sidewalks allow for the concrete to expand in the summer and contract in the winter without cracking the concrete. So different substances expand at different rates, and this is used in bimetallic strips. So if you have a bimetallic strip of brass right against iron, well, it turns out that there's a greater thermal expansion for brass than there is for iron. So if you cool a bimetallic strip, the brass will contract more than the iron, and it'll bend up towards the ice. Room temperature, the bimetallic strip might be straight, but if you heat it, then the brass will expand more than the iron will, and it can bend it the other direction. So bimetallic strips will bend different amounts depending on the temperature, and that can make a thermometer. It can make something that will turn on or off a heater or an electric toaster by making an electrical connection based on the temperature. So there is one exception to the rule of thermal expansion. Normally, you heat something up, well, it expands. Well, the exception is when water turns to ice. When water becomes ice, the temperature goes down, but it expands. The volume goes up. So that's because of just, again, the crazy water molecule. It has this open crystal structure that results from these strong bonds at certain angles. So this makes ice less dense than water. And Hewitt shows this rather complicated graph which just shows the volume of 1 gram of H2O versus the temperature. So ice has 1 gram of ice has a volume of about 1.09 milliliters. If it melts and becomes water, well, that volume drops down. It becomes more dense. And if you zoom in on this little part, you will see that the density continues to increase, so that the most dense temperature for water is plus 4 degrees Celsius. Then if you keep increasing, the water gets less dense again as it expands. It continues expanding until it boils, and then water vapor has a very, very low density. So when ice freezes to become solid, its volume increases tremendously. If you cool solid ice further, it will contract a little bit, but the density of ice at any temperature is still much lower than the density of water, which is why ice always floats on water, something that this polar bear knows pretty well. Okay, chapter 16 is all about heat, conduction, convection, radiation. And we'll talk about Newton's law of cooling and global warming and the greenhouse effect. So to start off, any objects that are in thermal contact and have different temperatures will have heat go from the higher temperature object to the lower temperature object. And there's three modes of heat transport: conduction. For example, the fire is hot, your hand is cooler, and so heat will be conducted along this iron rod. There's convection, so actual currents of air can carry heat from the fire to your hands, and radiation, which is where electromagnetic waves carry the heat from the fire to your hands. So we'll start with conduction. Conduction is the transfer of this internal thermal energy by electron and molecular collisions within a substance, especially in a solid. So the molecules are vibrating a lot in this floor. If your feet touch, then heat will be conducted and into your feet. So good conductors of heat conduct the heat quickly. And it turns out that metals conduct heat better than a lot of other objects. So a copper kettle will conduct heat from the fire into the water. Poor conductors are called insulators. These are substances in which the electrons don't move freely. And so good insulators include glass, wool, wood, paper, cork. This styrofoam cup, if you touch it, it has the heat going very slowly from the coffee out into your hand. So insulation doesn't prevent the flow of this internal thermal energy, it just slows the rate at which internal energy flows. For example, this pink fiberglass insulation in the walls will reduce the rate that heat flows from the higher temperature side to the lower temperature side. Convection is the transfer of heat involving the bulk motion of fluids. For example, in this room, you might be able to see a visible shimmer of air above the radiator, and that's actually the air moving and carrying heat around. You can also sometimes see visible shimmers of heat currents in water, for example on this pot or above this heating element. The reason for convection is that the warmer fluid expands, becomes less dense, and is buoyed upwards. And it rises until its density equals that of the surrounding fluid, and then it will fall again when it gets more dense. This can cause winds. So when the sun heats the ground, the temperature of the land rises faster than the temperature of the water because of the higher specific heat capacity of the water. So what that can do is it can create higher temperature, less dense air over the land, which will rise up until it cools, and then it'll drop over the water, and this is called an offshore breeze. At night, the ground will cool faster than the water, again because of the high specific heat capacity of water, and then the air will be cooler over the land and fall. It'll raise to a higher temperature over the water and be buoyed upwards and create an onshore breeze. And lastly, radiation is the transfer of energy via electromagnetic waves, such as light, radio waves, infrared waves, or light waves. So radiation, or electromagnetic waves, are waves in the electric and magnetic fields. And they exist as long as radio waves, okay, longer wavelength waves, all the way down to visible light. If you go shorter and shorter, it gets down to gamma rays. But these are all the same thing, just waves in the electric and magnetic fields. And it turns out that the wavelength is related to the frequency. Longer wavelength light, like this red light, has lower frequency, whereas blue light has a shorter wavelength and higher frequency. So every object, it turns out, will emit radiation if it's got some temperature. If it's a very high temperature, like the sun, it emits visible light. And if it's temperature like objects here on Earth, it'll emit infrared light. So when we look at somebody with our eyes, we're always seeing reflected visible light. But if our eyes were somehow sensitive to infrared, then we could turn off all the lights and we would see objects with higher temperature glowing in the infrared. So it turns out that as you raise the temperature of something, the peak frequency of the emitted light gets higher and higher, okay, higher frequency. So moving towards the blue. And here actually is visible light. So all of these objects are emitting mostly in the infrared. But as you increase the temperature to thousands of degrees, you see more and more visible light. So a room temperature object emits just mostly in the infrared. If you go above about 500 degrees Celsius, something will start to glow red. At about 600 degrees Celsius, you start to see it glow more yellow. And if you really increase the temperature to about 1500 degrees, it starts to look white hot. So any material that absorbs more than it emits is a net absorber. If it emits more than it absorbs, it's a net emitter. And this net absorption or emission depends on the relative temperature of the object to its surroundings. Okay? So if this stove is hotter than its surroundings, then it'll be a net emitter. If it's cold and the room is warm, it'll actually absorb. And that's why it looks black. And it turns out that anything that is black like this, a good absorber, is also a good emitter of electromagnetic waves. And poor absorbers are poor emitters. So any surface that reflects very little or no radiant energy looks dark, like eye pupils, open ends of pipes in a stack, open doorways. Okay, the light goes in, but it doesn't come out very easily, and it can look dark. Good reflectors are poor absorbers, and poor absorbers are also poor emitters. So it turns out that a white container does not emit as much electromagnetic radiation as a dark container. So if you take these two containers and fill them up with a very hot fluid, then the dark one will cool down faster than this more reflective one. Newton's law of cooling is that the rate of cooling is proportional to the difference in temperature between the two objects. The coffee's hot, your hands are cooler, and so there's a temperature difference. The greater the temperature difference, the greater the rate of heat flowing between the coffee and your hands. Also applies to the rate of warming. So a warmer house, if you crank up the heat in your house, it leaks more energy to the surroundings than if you have it less warm. Also, frozen food will warm up faster in a warm room than if it's in a cold room. And lastly, I want to talk about the greenhouse effect. So in an actual greenhouse where you keep flowers, short wavelength radiation from the sun is transmitted through the glass. Then it's absorbed by the flowers and it's re-emitted as infrared. And it turns out that glass does not transmit infrared. It just reflects it back in. And that's why a greenhouse will warm up. So there's also greenhouse gases. So the air we breathe is mostly nitrogen and oxygen, which is transparent to both visible and infrared light. But certain gases are transparent for visible light, we can see through them, but they are absorbing for infrared radiation. And these are called greenhouse gases because they act a little bit like the glass of a greenhouse. Examples include carbon dioxide, water vapor, methane, and nitrous oxide. A lot of these are produced by the exhaust of cars, so pollution as a form of greenhouse gases. So here on Earth, what happens is energy is absorbed as visible light from the sun, and then it's partly re-radiated by the Earth as infrared radiation. And some of this terrestrial radiation is absorbed by the atmospheric greenhouse gases and then re-emitted back to Earth. And so the equilibrium temperature of the Earth is determined by how much greenhouse gases are in the atmosphere. More greenhouse gases means the temperature of the Earth has to be higher in order to make the power balance coming in from the sun and going out from the Earth. And so as human activity has been, over the past couple of hundred years, has been steadily raising the amount of carbon dioxide in the Earth's atmosphere, this will actually contribute to global warming. So here's a nice little graph including some direct measurements of the carbon dioxide concentration in the atmosphere. In historical times, it has hovered around 250 parts per million by volume. This is up to the last couple of thousands of years. Over the past couple of centuries, it's gone up by about 50% and is now somewhere about 380 parts per million by volume.